Cool. Hello, everyone. Thanks for coming along to the talk. You won't have to dance, don't worry. I guess if you feel like it, you're welcome to, but it's not, there's no mandatory audience participation. So just one thing to say before I get started with the talk proper. As you might be able to tell from the slide there, I work for a company called ThoughtWorks. So we're hiring enthusiastically in both Madrid and Barcelona. And if you're interested in programming languages, but also in agile development, then please consider giving us a call. Cool. So the story I want to tell today is about a very specific kind of what you might almost call ethnic music. And by that I mean music that is connected to a particular kind of cultural context. So traditionally in universities, there were two kinds of music studied. There was normal music and there was ethnomusicology. So normal music is somehow considered to be universal. Ethnomusicology is for people with, I guess, non-European cultures. But when I say I'm going to talk about a particular kind of ethnic music today, I'm actually talking about that European tradition. So that idea about what makes music good that started with the ancient Greeks, worked its way up through Greek colonies, up the Italian peninsula, through to Germany, Austria, and the rest of Europe. So I'm going to trace back what I'm talking about today to the Pythagoreans, actually. So you might remember from high school the idea that a squared plus b squared equals c squared, where c is the hypotenuse and a and b are the other two sides of a right-angled triangle. That sect of people, they were mathematicians, but it might also be more correct to call them numerologists. So they didn't just calculate theorems. For them, numbers were also a kind of a religious and aesthetic matter. So there's a famous story of the Pythagoreans where the person who apparently, he or she, discovered that if you take a right-angled triangle where both the sides are 1, that the hypotenuse is the square root of 2, in other words, an irrational number, a number that cannot be represented as the ratio of two other numbers, that person was effectively ostracized for blasphemy, right? They made this discovery because Pythagoreans, for them, whole numbers and ratios were the important principle of organizing the universe, the principle of what made things beautiful, of what made things pleasing to whatever god it was that they wanted. So when they found they couldn't do that, that was actually a matter for great ugliness. So the reason I bring up the Pythagoreans is that idea of music and proportion is one that European art music has taken its lead from. So other kinds of musics will have other kinds of rules. They may be similar to what I'm talking about. They may be different. They may have other interesting features. But in European art music, the overriding imperative was to design a system of relationships that lets us play lots of notes at once in a way that's really interesting, right? So harmony, notes at once, that kind of proportion is what I'm going to talk about today. Before I get into playing more than one note at once, of course, I want to just cover what one note is. So I want to just try to demonstrate playing a sine wave for you. Hopefully that will work out. Whoops. No. That wasn't part of the... Yeah. Sorry, just let me check. Not really sure. It's not supposed to be part of the demo, but I guess that's an inevitable part. Okay. Sorry, I've just been messing with the volume and stuff at the last minute. So here's a photo of Chris just as he's trying to code in front of an audience when he's made a mistake from it. So I'll try again with just slightly lower volume, because that was very loud. Alright, so you can hear that sound? Cool. So let me cut it off. That's not a very pleasant sound, right? Because neither changes over time, nor that has more than one frequency playing at once. But as you can see from the 400 here, that is playing a pressure wave that oscillates at 400 times a second. So every 1 second, the amount of pressure goes up and down. And interestingly, for Pythagoreans, for whom triangles and angles and things like that were pretty awesome, the sine wave actually follows a very similar principle to when we're calculating triangles. So I want to try playing two waves together because these two waves that are very close together will have an effect that I think you might find interesting. You can hear how it's pulsating. Now the reason it's pulsating can actually be explained with your high school geometry. So when you have two sine waves, you can express two sine waves that are added together as the multiple of two sine waves. And the multiple, although I won't go through the trigonometric identity exactly, but the multiple of the sine waves is a combination of the difference of those two waves multiplied by the sum of those two waves. By the average of those two waves, I mean. So in the case of waves that are very close together, you get this effect of a wave that sounds like music multiplied by an oscillation of the frequency. Cool. So the closer you get, the slower this effect is. Cool. Just getting a little bit of cut off, so I might try to lower that volume a little bit more. Now you get that same effect when you have realistic instruments that have funny shaped waves as well rather than pure sine waves, but it's a bit subtler. So if I'm going to play an organ sound, hopefully that'll sound properly, and then you should hear a bit of throbbing as well. So you can hear kind of waves getting louder and softer. It's much less distinct though because an organ isn't a pure sine wave, it's made up of many sine waves together. Cool, so when you let me just open up. So when you have a musical instrument, what you're doing is controlling the frequency played, right? So each time I press a button and blow, I'm causing the reed within to generate a sound wave, and I can control that. But you might ask yourself, well, I've got buttons here, right? There's no sliding scale, but the frequency is theoretically could be anything. So what is it that determines which frequencies should be on the keyboard, have a button, and which ones don't? And that's what I'm going to get into a bit. So the answer is about something called consonance, so the relationship between multiple sounds. So if you play two frequencies that are the same together, I guess you just get the same thing back, maybe a little bit louder. Sounds very smooth. Now the interesting thing you get is when you start playing things that have simple integer relationships between them. So this is kind of where the Pythagorean ratio concept comes in. So here's what happens when you play 400 and 500 at the same time. Right, you can hear kind of relationship. 400 and 600. This is a very smooth one. So 400 and 600, that's, I guess, the organizing interval of Western music, which is the ratio of 3 on 2. Let's try 400 to 700. It's a bit more awkward, but if we resolve it to 400 to 800, sounds quite nice. So the other most important relationship that we should base all our study on is that a ratio of 2 to 1 counts as equivalence. So if you're playing like a note and you go up what's called an octave, you're doubling the frequency and you're hitting another note that is in a musical harmonic sense equivalent. So if I play them together, they harmonize so well together that harmonically we consider them the same thing. This is quite important from a cultural point of view because male voices can typically produce wavelengths of up to twice as big as female voices. So if you want a group of mixed gender people to be singing the same song, you can't say it has to be exactly the same frequency, but you can say that if they play two notes that are double or half the frequency of each other, that they kind of count the same. And so that's what we're culturally trained to do. Most cultures have the same thing, where that octave relationship is considered equivalence. So I'm going to try going back to our old friend, the square root of 2. So what happens if we play a ratio of the square root of 2? Let's see. Right, it's really kind of awkward, right? So let's play the nice one again. That's nice. This will probably sound a bit weird. So that's literally known as the devil's interval from later times, where you can see that we've kind of taken our lead from the Pythagoreans. So the same number that got someone kicked out of Croton in southern Italy, the Pythagorean colony, was also in medieval music. Not so much an object of blasphemy, but something that really didn't feel like it came from God, like it came from the other place. So I'm going to discuss how we get to this idea of buttons on a keyboard. So I'm being a little bit anachronistic so far because the Pythagoreans didn't have keyboards. But the really nice thing about the keyboard, let me just switch back to photo booth so we can see, is that it lays out the notes that we can play in a really obvious linear way. So if you're going to play a guitar or if you're going to play a clarinet, you have to know how to play them to translate that user interface into a model, whereas a keyboard is a really nice natural mapping of the properties of sound through to actual physical thing. So I said that the ratio of 3 to 2 was the important one. So in the octave, which is the space between a frequency and its double, we have, well, 11 notes plus the 12th being the final octave. And the principle for how those get generated actually in a kind of a mathematical sense, is that we can continue to start a base frequency and multiply it by 3 on 2, and then keep doing that process, halving as necessary to get back inside the octave. But I'm not supposed to play that one, so... So eventually, when you play enough of these games of multiplying by 3 on 2 and then halving to get back inside the octave, you hit all 12 of these notes and you return back to 0. And if you're good enough at mental arithmetic and you can spot a flaw in that, then you're reading ahead, because I'll get to that in a bit. But practically speaking, that's how you generate the notes. So you start from a fixed point, and in music all we care about is ratios. We don't actually care about absolute values. So eventually you'll loop back around to the start. So if you want to play those intervals because they're really pleasing, you're reduced to a game of, well, how do I set up a system of music that it gives me the best opportunity to play simple ratios? How do I select my notes so that happens? Well, to start with, what needed to happen is that musicians needed to understand that that's what made things sound good. And this is where Pythagoras is credited yet again. So you probably find, if you do readings of the Pythagoreans, that Pythagoras as an individual is credited with an awful lot of achievements in an awful lot of different fields. So probably what happens is that you have a legendary founder of a movement is credited with things that were just general knowledge among the people who made up that sect. But anyway, Pythagoras, walking through Croton, is supposed to have walked past a blacksmith shop and been listening to like the hammers crashing down on the anvils. And he observed that what he heard actually sounded musical. So what was it? Was it that, and it wasn't the case that he knew that from the rest of his life that any sound sounded musical, but he just found that those particular ones did. And in fact, even more interestingly, he found that some of the anvils sounded musical and harmonic to him, but there was one that didn't. One that sounded off, much like that devil's interval that I played before. And so when he investigated, what he found was that the ones that sounded harmonious had, as a size, a simple integer relationship between each other. They were either the same or double or 3 and 2. And that the one that didn't sound good was of a random other size. So understanding that, Pythagoras took the lead in trying to design a musical system that would take advantage of that insight and allow people to be maximally harmonic. And you can see why this is interesting, because we don't just have to stick to there's two relationships between sound, right? We can play, if we want, that's kind of like a straight line. If what we want to do is play really interesting sounds, which is very common in Western art music, we actually want to pick 3 sounds, and they will therefore have 3 relationships. So it's a very kind of complex thing to pull apart. It's something that we find quite interesting. So it turns out that if I take 3 frequencies, 400, 500, and 600, we get what's called a major chord. So that sounds really nice, because each of those, the 3 relationships between these 3 numbers, kind of in a Pythagorean sacred triangle kind of concept, is all good. If I was somehow to just randomly mess with it, it starts to go kind of weird, depending on whether I accidentally pick another relationship. So that's what's called a major chord. And so you probably noticed before when I was playing this that some of the notes, the ones that the black notes have stickers on, and they have different coloured stickers. So why is that? So it turns out that if you take a starting point, you can make a major chord with it. But you want more than one chord because as ethnic Europeans, or as people who are following that music tradition, what we want is to create sounds that we can change over time. So the principle is that the yellow notes form one major chord, and they have the same relationships within them. But you can also take a similar set of relationships starting from the point of any one of the other yellow notes. So if I think about like these 1, 2, and 3 notes of the yellow chord, I can also form another chord by sharing this note and going a relationship of 3, 4, 5. So these two chords both sound harmonically sane together, but also so within themselves, but also in a relationship. So what we're seeing is that the notes of a scale, in other words, the notes that a single piece of music will typically play, are related by these ideas of triads, and these triads share particular notes. So there are chords that have simple integer relationships between each other, and then they have connections between them. Now, that's a major chord that I played now, right? 4, 5, 6. Now I'm going to play what's called a minor chord. I'll play a major first, and then contrast this with a minor, which to our ears sounds kind of sadder. Well, that's why it's kind of minor. But you might wonder whether I've been entirely accurate with what I said, because I said chords and harmony are based on simple integer relationships. But you can see that there's this 416.6666, 500, and 625. So what's going on there? Well, it turns out that major chords are based on simple relationships between frequencies, but you can find that minor chords are simple relationships, in fact the same relationships between wavelength. So if I convert from like meters back to hertz of 6 on fifths meters, 5 on fifths meters, and 4 on fifths meters, I get this same minor chord. So you can see the 4, 5, 6 sitting in there, but it's actually hidden because the principle is that it's based on wavelength rather than frequency. If you're, I don't know if this is how easy this will be to understand, but if you think that we're talking about ratios, so how do you convert from frequency to wavelength? Well, it actually involves an inverse relationship. And so an inverse relationship when we're talking about ratios is equivalent to flipping a chord upside down. So you can see I've got from a bass note of the major yellow chord, 1, 2, 3, 4 notes to get to the middle note, and then 1, 2, 3 notes to get to the top one. If I flip that around, I should get a minor chord. That's what I get when I kind of rotate the chord, the interval, from here across to this side here. So turning a major chord upside down, so I guess turning that frown upside down, perhaps, if you're thinking about the minor and major chords, lets you convert between the two. So what we want is an opportunity when we're composing songs, or for our musicians to compose songs, that they get as many opportunities to play these chords as possible. But this is where I need to introduce to you the bad guy of the story, and the bit that makes the math not add up, and the bit that we have to use our human ingenuity to overcome. So I'm going to refer to this as Pythagoras' bane, but actually this is normally called, somewhat poetically, the Pythagorean comma. So what is the Pythagorean comma? Well, the Pythagorean comma is, well, literally what it is 3 to the power 12 over 2 to the power 19, which is, if you can't see at the bottom there, 1.01364. So it's not quite 1. So this is what we get when we take our octave and continually try to jump up by intervals of 3 and 2, and then every now and again halve again. The closest we get reasonably to getting right back round to where we started is still out by this Pythagorean comma. So there's a point at which we can't make safe integer relationships. Now, the scale that I'm talking about, again, is Western European scale. There are Arabic scales that have more notes in them that get closer to the 1, but I'm going to be talking about this 12-note scale that we generally hear in Western art music and pop music as well. So what are you going to do with this Pythagorean comma? I almost think of this comma as like a pause, but like the awkward pause after you've explained something you thought was really going to be good, and you just understand there's a slight disadvantage to it. So I can imagine Pythagoras kind of coming back after his visit to the anvil, back to the other Pythagoreans, and talking about how he devised this system of music. It was great. And then just, it works completely. It's great for harmony. Pause, Pythagorean comma. But there's this problem with the mathematics. 3 and 2 are relatively prime, and there's no way to go round and round with relationships of 3 on 2 and halving that gets you right back to the start. So we've now got this problem. We've got this tension between what we humans aesthetically would like to hear and what is mathematically possible. So this is, I guess, an interesting invention rather than discovery kind of mathematical feature, because what we're about to cover next is not what is inherently the case with prime numbers or anything else, but it's how human musicians have responded to this challenge. So the Pythagorean tuning system deals with the problem by hiding this one Pythagorean comma in one particular relationship on the keyboard. So there's like one point on the keyboard. I can't play it on this one because it's not Pythagorean. There's one point that sounds really off. So you can see, if you look at this closure here, that a pure interval is 3 on 2, and we stack up our fifths with pure, and we hide one wolf tone in there. And yes, wolf tone is the name for it, because people are quite poetic about these things. So the secret to this is the wolf tone is the pure interval divided by the Pythagorean comma. So when you include the wolf tone, which is off, annoyingly so, you get back to the start. So that's one way of doing it, and that gives you a music that's really good at playing pure fifths, so long as you can reliably say that you can pick one of your notes in your scale, or one interval in your scale, that you're not likely to need. And that was okay for the music of the Pythagoreans, but it won't be okay forever. Another kind of musical way of coping with this Pythagorean comma is called mean tone temperament. So as we get into the Renaissance and Middle Ages, there's all sorts of other new systems devised to overcome the comma. And the mean tone temperament was based around the idea that in the medieval music, rather than the fifth, the third was, at least for the people who designed this system, a really important interval. So, so that was kind of a really pleasing interval to them. So what they decided to do was to sacrifice the pure fifths in order to get a better third. So in the Pythagorean tuning system, the middle note of the chord is separated from the bass note of the chord by a ratio of 27/16, which is kind of beautiful, but also a bit complicated. So what they wanted is one that was 5/4. Nice, real, simple, strong. And so in mean tone temperament, they have a bunch of fifths that are a little bit narrow so that the third will work out really nicely. They also have an even worse wolf tone that they're hiding among the sheep there. So I'll play some demonstrations in a second, don't worry. This is what we've done in our modern, bland McDonald's age. We've invented something called equal temperament. So once we get to the period of Bach, we can no longer reliably pick two notes on the keyboard that we don't want to play together. So we used to have this reference point, and we'd play all our notes reference point, but what Baroque music and Bach started to do was started to change the reference point and change the scale within one particular piece, which is where we get a really interesting key changes, really interesting Baroque music. So it was no longer safe to say that you had a keyboard that was great for everything except B flat to E flat. That wasn't going to wash because you're going to need those two. So equal temperament is based around the idea that we launder the Pythagorean comma smoothly throughout all the fifths. So they're all a little bit flat. So every one of the fifths is a little bit narrow, but it turns out that they're close enough to being okay, because they've only got a 1/12 of the comma in each, that it works out. And that's what we use in our kind of modern music today. So it's kind of cool because it gives you more harmonic possibilities, but it's also a little bit kind of bland and less quirky and wonky as the other systems we discussed. So I've talked a lot about the ratios, but obviously you should be able to hear it, right? So first of all, I'm going to play an interval of a fifth, which will be one of the fifths that's under warranty, one of the fifths we expect to play in the key, played in the 3 tuning systems. And they will sound quite similar, so you'll have to listen for that throbbing that we heard before when we had 2 notes that were not quite in sync. It's Pythagorean, completely flat. Mean tone, a bit wonky. This final one is equal temperament, which is probably for this purpose just as good as a Pythagorean. So I'll play them again. So the mean tone, remember, they've sacrificed that fifth, that 3-on-2 ratio, because they don't really care so much. So that one, the middle one, should sound the worst. Completely perfect. Little bit of a ring. There's a little bit of a throbbing in equal temperament. But let's try playing the fifth that isn't under warranty, the one that in those scales they thought they wouldn't need. That's a wolf tone, right? That's another worse wolf tone from mean tone temperament, and equal temperament copes just as well with this one as all the rest. So you can see that it is a difference. I don't know how well you're used to listening to intervals, but it does make a difference. So what I want to play is an actual piece to show you again the difference between picking tuning systems. So this is a closure code rendition of Row, Row Your Boat in B flat major. So what this should, I think, if I remember which key it is, if we play this in mean tone temperament, this should not work very well because it's going to hit those not under warranty intervals that mean tone temperament has. Very kind of soupy and flat, right? Kind of awful, yeah? It's supposed to be, don't worry. So now I'm going to play it in the key that mean tone temperament is good for, and what we should be able to hear is these ringing out thirds that are really awesome and the strength of mean tone. Much more harmonious. So you're hearing this kind of third being hit 3 out of 4 emphasis notes. So it does make a difference. Obviously, the intricacies of this depend on musicians to know exactly what's going on, but definitely the audience would know what they liked, and they probably would like the second one better than the first one. Although, it does depend. These things are cultural conditioning, so it's entirely possible that another musical system that might sound off to you would sound really nice to the person who grew up in it. So another thing that I want to talk about, so I said I advertised this talk as being about dueling keyboards, right? So I've talked a bit about the different ways that we can make these buttons map to exact frequencies, and I've used closure and my other keyboard to demonstrate that. But it also got me thinking, if we accept that we've got this history of an interplay between mathematics, musical technology, and musical culture, of going from Pythagorean tuning to mean tone and well temperament and to equal temperament, what does it mean that we make music with a computer keyboard, a QWERTY keyboard? How does that influence our musical practice? What's the co-evolution there? Well, the kind of hook that I use for explaining that to myself is something called Kolmogorov complexity, which is about how brief a description can you give of a particular string or piece of music? How compressible is it? So what's the shortest program you can write that would generate it? So it turns out that, if you have something like this air on a G string, which is a cover of a Bach piece, there's a lot of Gs, right? So if I were to type that out or to play that 1 G at a time, you can see it would take a very long time. So I've got just a little bit here where I say, okay, so the description length of the error on a G string, if I calculate it with a closure macro, is 15, and the result length is 2001. So it only took me 15 characters to type the code for doing it, but the actual result is 2000. So that tells me it's really compressible. You can come up with a really simple rule that takes you from 1G to 2000. Row, row, row your boat is also, as I've written it, similarly compressible. So it took me 347 characters or symbols to type that, and then it takes over 3,000 notes when you actually play it out. So why is this important? Well, I think that my thesis is that music from a QWERTY keyboard as opposed to a musical keyboard is less literal. It can unfold. It's like you can create a pattern or something that's like a seed and will unfold into a really intricate flower. So what you get is computational music. So anything where you can make a decision that is a simple decision but unfolds over a piece of music is something that our computational powers can help us with. So whether it's filters working on electronic music or repetitive beats or really interesting effects, that is what the other keyboard of the dueling keyboard is good at. Striking time. Let's give a brief example of this. Shut that file. So I don't know if you've ever heard of like Dueling Banjos. It's a song from the movie Deliverance, starring Burt Reynolds, who recently passed away, sadly. But in Dueling Banjos, there's these two people with musical instruments who are echoing what each other's doing. And so they're able to do that because traditional instruments, where you make one movement to play one note, are really good at responsive, quick, real-time decisions. So they play, reply to it, play something like this. Sorry, that's a bit too loud. I don't know if I can adjust the volume down. So just try it again. Hopefully indulge me if it is loud. The master volume seems to not be adjusting it there. Just a second, because that's not going to be pleasant if we try to play that. Let's try again. Be careful with your ears. Okay, cool, much better. So the reply to that would be but because this is computational music, I can do things like, with only a small amount of extra elaboration, I can start to make it play multiple times. So I could make that play times 2. And again. So each time I want to play a new note with this, I have to take a new breath. I have to press the button again. But with computational music, I can actually generate an indefinite number. So let's try, you can watch me type a little melody, which will take a little bit of time because it's not very good for typing melodies, which is also from Dueling Banjos. Oops. And I'll map that across a blues scale. So the melody itself took a while to do. Oops. So you can see me just kind of playing around with replying, because I could make real-time decisions with this. It's actually a lot harder when you're typing algorithmic music to make that real-time decision. So, I want to close by playing a piece of music that's designed for this concept of both having real-time input from a keyboard here and, I guess, computational unfolding input from Vim here. And then we'll be done. Hopefully the volume will work on this, but I hope you'll indulge me if it doesn't. Very easy to do kind of like repetitive beats and patterns like that when you're in computational land.